So now we'll move ahead with our technical session 2. Our resource person for this session is Mr. Hillol Biswas, sir, currently serving as advisor in Power Division at WAPCOS Limited. A very warm welcome to you, sir. So before beginning the session, I would like to introduce our esteemed speaker. Mr. Biswas brings over 30 years of international experience in the power sector, renewable energy, and technology applications, having worked across several countries and 4 continents. He holds 12 master degrees in AI and machine learning and quality control, and has additionally completed a postgraduate programs in neuroscience research from internationally recognized institutions. He is senior member of IEEE and is associated with several academic and professional bodies, including the Indian Society of Remote Sensing, the Computer Society of India, and the National Academy of Psychology. He has served as an author, reviewer, and evaluator for international conferences and journals published by Elsewhere and Springer. We are honored to have him with us today. So now with this, I would like to request sir to please take over the session. Thank you.
Yes, please. Thank you very much. Can I share my screen?
Yes, sir.
Okay, just let me check. Yeah, just if you give me a shout if it is visible, please.
Yes, sir, it's visible now.
Right. Thank you very much. I think the topic is vast. I would like to quickly delve in a little bit on this wind farm. Actually, wind farm is of 2 types, onshore and offshore. And little background that it is part of DER, reduce carbon emission, decentralized generation, improve energy resilience. So and of course a little bit of computational paradigm. We have a little bit of data analytics, cyber security, and should time permit, I know the time is limited, so we'll like to delve in that how this alternate computing, that is smart computing comes in, particularly quantum computing that is having a unique capability. So quickly layout I have contemplated. I don't know whether time will permit, but it's part 1. So we'll give a brief overview of wind turbine and wind farm. And of course, that has got 2 components, onshore and offshore. And part 2, I'd like to give a little bit demo of this, how wind farm SCADA database analytics are carried on and what kind of data are there. And part 3, again, should time permit, else my apologies. So the little bit of this wind farm cybersecurity aspect. So let's start with. So part 1, this wind turbine and wind farm. So brief interview. Then actually, I think it's probably 5 or 6 days FDP who are already quite, saturated with this AI ML parts and everything. So I won't go into forward that. But because wind farm is not so unique, uniquely prevalent, at least in our country. So I'd like to give a practical overview from the IC. That's the 61400 series, is comprised of many parts and little bit of this relevant to this thematically for this conference, FDP. So let us see how it goes there. So quickly, if we quickly go into there, it's 1991, Vindby, Denmark. That was 5 megawatt offshore wind turbine. That was the start. And in UK, that was the first wind farm, Bleath. Of course, it's a very small 2 into 2 megawatt. And later on, many has come up. So quickly, if you see on the right-hand side, so till few years back, this United Kingdom was quite dominant in particularly offshore wind, but obviously not unsurprisingly, China has overpassed so many countries. So recently, even 15 megawatt single standalone offshore wind turbine has also been introduced, probably commercially as well, that has passed the scenario certification. So quickly, what the resources are, it is all about collecting the wind and getting the wind power available. This is just like power potential studies, also wind potential studies are carried out, and end of the day, we harvest this wind offshore and onshore wind. So here quickly that if we could see that different maps, but just it is middle of the sea almost. So that is the difference with the onshore and offshore. And left hand side bottom and right hand side bottom. So these are wind rows. That means wind availability both from the values as well as the magnitude as well as the direction. So optimization is a trade-off between wind turbine generator plus transmission networks plus the substation. And just like onshore substation, we do have offshore substation as well. And there are many parts of that, and of course there are these failure rates, repair time. These are quite little bit factored in for different regime. So cost effectiveness, it's the layout optimization. There have been micro seating of wind turbine, wind farm, electrical system. So these are all parts of that. Current trends and research perspective, micro seating of offshore wind turbine, quite heavily, optimization technique, electrical collection system, and of course, cyber security, that's also quite dominant these days. So what's the difference with the offshore wind current trend? It's a layout optimization. Just quickly, if you see on the top of right-hand side, so there have been three, this dot matrix kind of thing. These are nothing but the offshore wind, offshore farm layout. So on the first one at A, that was just like an array of square matrix. And B, if you see it is a little curvilinear, and C, it is quite typical shape, and it's all because of this this management of wake effects. Actually, wake due to the wind effect on the upstream turbine that affects the downstream turbine. So effectively, we tend to get a little bit of smaller amount of this offshore wind power in turn than we could have expected to. So this is something on the satellite imagery that could peek out on the right-hand side. If you see, these are something called the wake effect because the wind induced this disturbance on there. So this is quite a typical offshore wind farms and the connections. The left-hand side is AC connection and right-hand side is DC connection. So quick overview. And of course, these are Great Britain of National Grid, in United Kingdom layouts, left-hand side 400 kV, also right-hand side. So typical, so just to give a flavor that both HVAC as well as HVDC connections are there. Many European offshore wind farms come out. It is a little bit of backdated data up to 17, quite at least 8 to 10 years back. But these are different kind of generators, DFIG, PMSG, SCIJ, this kind of thing. So every country, they have quite dominant today. Particularly these European countries, you see that UK have been dominant, but Germany, Denmark, Belgium, Sweden, they are also quite heavily coming up. And the other differences, just to give a quick overview. So wake effect, layout optimization, height of wind turbine, the structural health monitoring. So these are all the imperatives, both for the short, middle, as well as the long-term implications. And of course, end of the day, in the back end, there have been data analytics. Of course, you are already familiar with AIML and this thing. So this is a quick overview of this UK. UK is having three parts actually, Scottish part, where the networks are quite green. Mostly dominant. They have two utilities, Scottish and Southern Energy Network and the Scottish Power Energy Network. And they have quite extensively harvesting these, and just a quick map of capacity factors for those two reasons. On the left-hand side, the standard terms, the levelized cost of energy. That is a quick, simple example. Equation the capital expenditure into cost recovery factor plus operational expenditure divided by annual energy production. So that's a quick overview. So grid stability, this is very essential because unlike these other renewables, of course, in renewable, you are aware of this inertia is an issue. But here it's a dynamic stability that governs actually. So there have been many critical studies, and from the power system studies also, there have been quite extensive studies have to carry out apart from just conventionally in a conventional power system. We tend to do only few studies, is maybe more than sufficient, just like load flow, short circuit and insulation coordination. But in addition to that, there have been many studies including flicker, disturbance, and dynamic stability and this kind of things. In Indian scenarios, why we need to have a flavor of that? Because in India, we have an ambitious plan since last 2015, the policy have been in place, and the plan is to inject about 70 GW in Indian grid in I think 30 to 35, something like that. So particularly two areas that have been selectively chosen. One is the Kutch area of the Gujarat marine areas, and on the other one in the southern state of Tamil Nadu, there have been identified two pockets. So what's the, just to give a very brief overview, so what's wind? Wind is, as we know, is a school level physics because of the rotation of the earth. Wind is induced, and that have been quite extensive phenomena, but end of the day, when it gets, we harvest that and tend to have the wind power. So various wind tower structure, if you see on the left-hand side, there's a steel tower, and then the tubular concrete was there, lattice tower, three-leg tower, guide wires, so everything have been there. And this one is this offshore and onshore comparison. On the left-hand side, if you see, there's an offshore wind turbine, and on the right side is the onshore wind turbine. So just a quick comparison that how drastically things are different. So it's in case of offshore, these are gigantic structure, quite extensive, tall, and of course robust. And on this figure, if you see, it's an onshore substation left-hand side, and on the other hand, right-hand side is offshore left-hand, and right-hand side is onshore substation. Excuse me. So that's the different components of offshore wind turbines. So the difference is that it is right in the middle of the sea. So that's why there are many eventualities to take care of to carry out this kind of design. As we said, that Windwind Denmark was the first in 1991 for building the first offshore wind farm, but there have been many farms come out, and that was done by Ørsted in one Danish company, utility basically. Past wind farms, so we have already discussed this one. So just if you have a quick look, so how these structures have developed. On the left-hand side, in around 1980s or middle of 80s or 90 earlys, so this height of there, and now if you see, the Statue of Liberty has overpassed, and this 17 megawatt is termed, so it is about of course in a US unit, it is 495 feet. So roughly it is more than 150 meters, something like that, the blade size. Now, why we intend to go for offshore? Because of course it is green, but it is a trusted concept. The one thing is clear, the abundant amount of wind power available in offshore. So that's more rampant than the onshore. So that's why it is quite important to carry forward there. So certain advantages over that. The greater area available for setting up larger projects. Of course, these days, wind farm projects offshore that spread over many square kilometers. So it is as good as 50 by 50 grid, in terms of kilometers. So where this capacity, including, a combined capacity of few hundreds megawatt is coming up. Then what is the practical implementation? We tend to delve on one IEC series, particularly that is IEC 61400, and there have been many parts of that. First one is design requirement, and then we have a small tower, a small wind turbine. A particular part 3 is of offshore wind turbine, and there are many parts. Part 12 is of this power performance measurement, and part 21 is electrical characteristics. And of course, there is one part 25, and those who are aware of in this industry, that is aligned almost with IEC 61850. that is substation automation system, but it is more specific to wind turbines. So, but it is almost analogous to that, and based on that, IC 61850. So this is 61400 per 25. Briefly, we tend to cover into there. So hourly variation of offshore wind speed, if you see, there are many curves into that, but one thing you could see that curves are more or less consistent. And this gives a quick comparison that how offshore wind could be harvested for this power evacuation studies. Yes, a very particular term is there that's called diurnal variation of wind. That means there is a day and night variation is there, and that drop is quite significant in terms of onshore. But in comparison, that offshore, the curves are mostly flat. So that's why one of the reasons of this exploring this offshore wind has been abundant. It's a quick curve of monthly variation or different band and for particularly month-wise. So that's almost steady state. This offshore wind. So globally, if you see this map, this I don't know how much it is clear in the net, but it is on the northern side of European seas. So if you see, these have been almost flooded with offshore wind farms. So almost every country that boast with the coastal areas into Scandinavian as well as this UK and Northern Irish. So these are already flooded with offshore wind farms. Typical offshore wind turbine generators, that's the main component. But if you see on the right-hand side, that has a very nice looking array on the middle of the sea, and they are built on just to carry forward the power generated back to the shore. Wind power density over the global oceans in winter and summer. So that's a quick comparison. This kind of these days remote sensing database things are available. So that gives a quite preliminary idea of how wind power potential could be studied for this generation of this power. So that's a quick wake effect. That means how this wake disturbs this wind flow, and this is actually satellite imagery. I think that's quite very small dot, may not be quite visible. So anyway, but what we intend to say that these are already picked up from even on the sea by the this remote sensing data. So this is quite extensive. If you see these wind farms and the wake effect, so this is how the front turbines could have impact on the lower turbines. I mean, those which are at the downstream. So there's a difference. The next thing is there have been a few factors to consider: this lightning, solar radiation, chemically active substances, salinity, water density, water temperature range. So these are some of the things. Lightning protection of wind turbines. So it's very important because these are very tall structure, and any tall structure, those who are a little bit familiar with lightning, studies. So it carries it forms a zone of attraction for lightning activities. So very naturally, it is, inclined to carry some kind of lightning discharge. So that's why the concept is to take a down conductor system inside the blades, actually from the tip of the blade, and that to carry forward through the wind tower, and right up to the bottom level. But what is distinct here in offshore wind turbine, we do not need a typical earthing grid or earthing mat like kind of thing because of the this wet soil, of course, all around the wind turbine. So earthing is quite abundant in case of offshore wind farms. So now we would like to go a little bit of flavor of this IC 61400 series, particularly part 12, which deals with this wind power performance measurements. So these standard actually have been prepared both for the manufacturer, purchaser, grid operators, as well as planners or even regulators tend to go for having this updated and refined approach for this way offshore wind turbine, and of course it also onshore wind turbines as well. So overview of a test method. There have been many test methods to certify what kind of this wind turbine is, particularly for this certification purpose, because there have been many distinct certification criteria. Just IEC also, they tend to certify the wind turbines, both onshore and offshore. And in there is a concept called natural anemometry, because they tend to have an anemometer installed on the nacelle part of this offshore, wind turbine, and that it tend to collect the data of the wind, and in term to end of the day certify what particular megawatt of this wind turbine it characterizes to. So that's the natural anemometry method, and that's part 12 is of course it is of about. So this gives that where the anemometer has to be placed for the meteorological tower, and of course on the nacelle itself, and depending on the terrain, or if it is a flat or complex terrain, of course that is applicable for onshore, but in offshore it is obviously this wet terrain all along. So in national anemometry meter, this wind is measured. The anemometer, as we have seen, this position is fixed, stipulated as per the IEC that we have to tend to carry forward. Turbines rotor and nacelle distort the wind significantly, so therefore it is necessary to quantify this distortion and to take into account. One more thing is there, that is an NTF, nacelle transfer function, that means through which we tend to factor that what kind of this wind, this proportion has to consider for the certification purpose. So this is all about power performance measurement and electricity producing wind turbines. It comprises of two parts. One is this national anemometry, another is meteorological mast, for which you have to specify and particularly install one kind of mast for the purpose of certifying the wind turbine. There are many symbols just like any other IECs. So this, I won't go forward to that, but let's skip these things. And what the electrical connection. So we, of course, wind turbine, the electrical connection is of imperative, and that shall has to be described during this procedure for this power characteristics curve. And this wind speed measurement shall be made, as we said. And there have been many other this kind of things. So wind direction is very important, and air density is also, and of course, because air density varies, as we are aware of, that it also impacts the electrical, dielectric strength of air. So that's why air density is very much important, because we have an electrical connection in there. So there's a formula is given, air density factor to take care of. So instead of taking a specific value of 1.225, or rather average of that, we tend to follow as per this IEC, this particular density curve. And end of the day, the reference wind speed that comes out through this formula, and this formula gives a different segment of that particular test apparatus. But end of the day, the density comes into picture, so that's why we have seen the formula, and this with respect to that, the reference wind speed is calculated. When test turbine is certified, of course, it needs the data analytics as well, and this linear regression analysis is more than sufficient, but of course, it comes with some caveat, and those caveats are, there have been some procedures called wind binning, something like that. Rotational speed and pitch angle. Pitch angle means the longitudinal axis through which the blade tend to adjust with respect to the wind direction. That's called pitch angle. And of course, there is an yaw angle. Yaw angle means as per the direction of the wind, it also tends to rotate, but it is again on the vertical plane. So, but this pitch angle, pitch mechanism and yaw mechanism, these are very integral part of wind turbine, and that's why rotational speed is also part of that. So one thing is there that's called binning. Binning means we tend to have a power curve based on the different wind speed available, but that wind speed has to be measured for the certification purpose at a specific interval of 0.5 meter per second. So wind speed bin width, that's IEC says that if we tend to develop a wind curve, that needs to follow this binning procedure at 0.5 meter, because for wind power curve there have been concept of cut-in speed and cut-out speed, and within these two where the wind power actually comes into picture. And there are some formulas into that, and just quickly overviewing through. So, and end of the day, ultimately, once we have this wind speed measurement, there we tend to calculate what's the wind power available. I mean, that's a specific formula is given as per IEC, and of course, that is taking into account the Bayes curve. That's 0.59 is a factor through which this wind can be measured and harvested. End of the day, annual energy production. Again, this is a little bit familiar with the availability. That means for 365 days in a year for 24-hour basis. So we tend to calculate what is the generic annual energy production, and of course this IEC gives that how to calculate that. So we are going through the formula itself. Just I intend to give a flavor that IEC particularly says this kind of formula to use for calculating that. But how high average annual wind speed should be this 4, 5, 6, 7, 8, 10, 11 meter according to this equation. So, and NH is the number of hours in a year. So we calculate 8760, and N is the number of winds, as we have seen, as a 0.5 meter, something like that. So power coefficient, that's all about. It's the simple equation, because we know power is just, if you see that, half into rho into A VQ, and the CP. So this CP is to calculate actually, because that gives that what your end of the day power factor of that this electricity generated, that will be taken into account, for that will be utilized for different purpose. And this gives, IEC gives that where we intend to have this place on the shaded area on the top side. If you see, it specifically says that anemometer has to be built in there. So that will give the accurate measurement. A quick overview, this is a met mast. If you see, it's an onshore scenario, and on the scenario, this number of these wind turbines are there in succession. But before that, the specific met mast have been prepared for, particularly for this wind speed measurement, and that will give ideally that rated power curve in terms of the rated power wind power turbine capacity. That means if it is a 2 megawatt or 5 megawatt or 6 megawatt, whatever it is, but the procedure is something like that. Based on this, the power curve is estimated. And this typical different components on the right hand side, top up, you will see there's a nacelle anemometer. On the left hand side, the whole thing is called nacelle. I mean, it comprises everything. There have been drive trains, there have been pitch control mechanism, there are brakes, there are gearbox, there are of course wind turbine generator. And on the left hand side, if you see, there are 3 blades, and on this every blade, the pitch angle has to be measured out of that, and those pitch angle may be different for different blades, but these are all the things through which every sensor will be placed into there, and every sensor is supposed to get back some kind of data, and end of the day we tend to have those data available through the secondary SCADA system, and SCADA system will feed you back at least few hundred parameters, few hundred of in terms of data analytics. If you say these are few hundreds of variables, at least 200 to 300, or for an offshore turbine, it clearly gives the statistical hours. So every parameters will have its mean, average, max, and standard deviations. So altogether, it's 1,000 number of variables are not so uncommon in terms of this offshore wind turbines. So that's why it's every sensor reading has to be taken into account, and that gives you the particular data analysis part, and what kind of this power is generated for the grid voltage frequency, but everything is contingent upon all the sensor data as a whole. So we would like to go in a little bit of that, but before that, that is the thing. So here it is a LiDAR-based wind speed recorded a mechanism. If you see this LiDAR data, and that tends to capture the wind speed in different forms. So, but of course, the site is in onshore wind speed, and that it gives. So, in general, MetBus gives you the undisturbed free stream wind needed for accurate power performance testing, and national anemometer sees disturbed flow, good for turbine operation, not for certification. Max permitted power, IEC says this has to be specified by the manufacturer information, PMC, but it needs to be verified. But the question is, how does the manufacturer specify this limit? Because there have been many parts of that, and it all comprises of how these calculated. So we tend to have a quick overflow there. So if you see this flow chart, so that's the, on the left hand side, it's a aerodynamic control, that is power coefficient, pitch controller. On the second column, if you see the mechanical limits, electrical limits, thermal protection, grid constant, and of course SCADA. And SCADA gives you the vibration, ice, yaw, error, everything. All together you come up, combined with a selector and lowest constant winds, and that gives you max permitted power. So max permitted power of a wind turbine, it is contingent upon many other factors, and it's a domain specific. So there have been both mechanical, then electromechanical, and this turbine system. So altogether it comes with how a manufacturer specifies that what the max permitted power shall be available. So what IC 21 in brief it covers power quality of grid connected wind turbines and method of measuring and reporting PQ, ensures turbine do not disturb the grid. So this is the characteristics of certification of the wind turbine, and this obviously PQ you are aware of, it's very problematic in terms of renewable generation, because wind, as we know, these are stochastic. So keep on giving some kind of estimate which may not be very firm. So, but end of the day, you have to sell your power to the grid, and the grid operator need to have their own this criteria of scheduling everything. So PQ, of course, it's the core area. So key areas: power quality characteristics, voltage quality, flicker, harmonics, RVC, dynamic electrical behavior. Of course, FRT is there. Key measurements: flicker, harmonics, reactive power and control modes, active powers, and ramp characteristics. Ramp, obviously, you are aware of. These days, even ramp rate is a talking point of even the thermal power plant generator as well, because when renewables are injecting into the grid, now thermal operators are asked by the regulators to go for a variable speed rather than the base load. So that is one of the things to balance the grid, actually. So it's a complex situation. Anyway, FRT, fault right through reactive current injection, voltage dip performance. So these the dynamic tests are carried out. And output report comes out with flicker, harmonics, RVC result, power reactive characteristics, FRT curves, performance, compliance summary, this kind of thing. Now, this has got two parts. One is for individual wind turbine, and second is for the plant level or wind farm, because in wind farm that can comprise of many wind farms, not necessarily every farm, every wind turbine. Often wind farm will have the same capacity. That means you could have a wind farm that comprises of different kind of wind turbine altogether. So that's the thing. So in terms, super short summary, just to give you a brief idea that how to measure turbine power quality, flicker, harmonics, reactive power, FRT. It ensures consistent reporting, grid compatibility, and fair comparison of the turbines. Now, when I see this Part 21 tests are performed, so during prototype or type certification, most common, during commissioning of a new wind farm, of course, in some countries, depending on their grid core requirement, after a major upgrade of control software change, And part 2 is a wind power plant as a whole. So it focuses on multiple turbines plus transformer plus cables plus substation, the whole wind farm. And this 21 is wind turbine level. So of course, as we have seen, end of the day, we get the wind turbine power quality test report. Now, part 21, 2, it gives at the point of intersection, the entire wind farm meets the grid. So, aggregate flicker from many turbines, total THD, we call it total harmonic distortion from the entire plant, then voltage dip and recovery at POI, plant level active reactive regulation, PRC, power controller response, frequency control behavior, short circuit, WPP, transformer collection system impact. What the output is WPP grid compliance, power quality performance report. So 21, part 1 and 2. So the difference is POI. That's where the plant level we need to look forward. So certify entire wind farm to meet the grid code, ensure compliant operation requirement used during commissioning, and of course grid acceptance. Purpose is to ensure grid stability even with significant penetration of renewables, which are inverter-based and behave differently than the conventional ones. Limit harmonics, disinjection, and flicker to avoid disturbance to the grid user. Demand voltage and reactive control to manage local voltage levels. Mandate FRT to avoid mass tripping of renewables during grid faults, which can cause broader grid instability or even at worst case could possibly cause a blackout. Ensure frequency support or response, especially as inertia contribution from conventional plants and reduces and renewable increases. Now, one of the things UK grid is considered to be mature in the sense, just is an quote in unquote. So they have this offshore wind, particularly over 20 years of high wind penetration, particularly Scottish and Southern Energy, Scottish Transmission Network. They are the first to early adoption of synthetic inertia, first frequency response, strict FRT curve, very detailed and model-driven certification process. They have clear roles, developer, OEM, power controller vendor, TSO, highly tested operational practices because UK grid is a little bit isolated. If you discard, of course, it is connected to a DVDC link with France and Belgium, but only a few HVDC. But again, the stability is very critical. In summary, it demands world-leading performance in frequency response, FRT, reactive capability, control modeling, because the grid operates with high wind penetration and limited system strength. So this is a quick comparison. If you see on the left-hand side, this is IC 61400 series for the requirement team. But the UK grid code equivalence, of course, there are something specific clauses there, but it is quite stringent. And what is the difference for them? That's a quick note is given. And of course, harmonic THD is there, interharmonics, disinjection, flicker, reactive capability, voltage control testing, reactive current injection, dips. So these are all the parts of that. Ramp rate capability, and then active power set point tracking, IC proxy. So these are some of the things. So LVRT, HVRT, again, IC plant test and UK test is quite different, just to give you a flavor. So that's, how system have been developed in that particular country and how it works through. Plant level models, CMT, RMS, again, something like that. Performance monitoring, back-to-back testing, IC requirement is specific, UK requirement is, again, little specific. So, in general, super short summary, 21 part 2 gives a measurement framework. UK grid code adds one of the world's strictest performance modeling and validation requirement on top of it. So, IC tests are accepted, but are not necessarily sufficient without the UK specific, some of the particular tests. Now, part 2, I would like to go for this little bit of rather practical demo. So there you could get what kind of SCADA data we tend to have actually. And that will give more flavor because IC standards, as you understand, a little bit of boring in concept to, but let us see that. Before that, I'd like to give you a brief overview that what these are actually. So in this part 2, we tend to have this power curve, active, reactive, AEP, annual energy production, but there are certain particular things which are called yaw alignments, voltage irregularity, then national transfer function, national power curve, etc. So that's the part 2, I mean, of the today's presentation. So we will delve into that. So before that, let us see what is SCADA data actually. So this is a quick flow chart. So if you see on the top right hand side, these are the operative. So it starts with your system, we have environmental system, we have thermal or auxiliary system, we have drivetrain, that's pure mechanical, we have status, only fault, only counter, we have generator and electrical, that's the bottom line. So your position, natural direction, this speeds, average, hydraulic pump pressure, gearbox temperature, this rotor and stator temperature, bearing temperature. So these are all the variables through different kind of sensors. The data comes into through the SCADA database, and through those database we have to ascertain that what the power curves are and what the, of course, we have to manage the grid stability as well. So these are the wind power plant, and which again depends on every wind turbine. So every wind turbine is got hundreds of sensors. So if you have a wind power plant, so you could just multiply and visualize that how many sensors are there, and in turn how many data are coming through. So it is unlike for a particular specific substation line interface. I mean, in substation you are aware that there is a process bar and this station bus IC 61850 and but in terms of so in case of wind turbines, things are quite extensive, and so many data are come into picture. Now, if you see, this is actually a quick overview in a pictorial format rather than this text format. There's drivetrain to SCADA. On the left hand side, on that upper part, this has got two parts. On the top part, it's the onshore wind turbine, and the bottom part is offshore wind turbine. So onshore wind turbine, if you see this rotor, main shaft, gearbox, high-speed shaft, generator, and of course we have electrical grid, and offshore a few component, but end of the day that we end up getting this SCADA data and this power map, power temperature, speeds. So these are comes into picture. So here is a quick comparison of this onshore and offshore parts. At the end of the day, these are all are interconnected, and we get the SCADA data, and those data tend to capture each and everything from there. So part 3, I also tend to cover a little bit of this means from cyber security aspect, those who are aware of, because these days cyber security is quite important, and it is being looked upon at the highest level so that we don't get end up some unexpected and some hazardous situation. So these things are something like that. So before that, I would just quickly like to see that this part 61,400, the part 25 is of communication, that is equivalent to SCADA of 61,850. And it has got again 6 parts. The part 1 is overall description. The part 2 is information model. The part 3 is exchange model. Part 4 is mapping to communication profile. Part 5 is confirmation testing. And part 6 is logical node classes and data class. And those who are aware of subsystem automation system, you know that this is logical node, logical class, these are there. But in case of wind turbine, these are very specific. So that's why we need to follow that. So conceptually, this 25, because all cyber security at some point, it has an interface with part 25. And this part 25, as we said, it is 61850. So same data modeling concept, logical device, logical node, data object, data attributes, same communication services, manufacturing message specification. We have goods messaging, sample values, web services, OPC, and same kind of mapping and interoperability guarantee, because you must be aware that one of the thing of smart grid is interoperability. That means every device that could gain or process the data they input, and at the end of the day, that could be interoperable by some other devices without or rather minimum human intervention. So that's the core concept of the smart grid. So interoperability is one of the crux of that. So information models. So these are things. Just to see this modeling approach. So entire thing on the right hand side, wind turbine and wind farm. So it is managed with this coding mapping. So we have protocol stack. We have logical node. We have different logical devices. Suppose WROT, it gives the logical node for rotor, and the speed and position. These are the two attributes we tend to get from in there. So these are some of the service model and the communication service interface, some kind of thing. So quickly go through there, and yeah, these are the logical node classes, because WROT, WTUR, XCBR, of course, you know, circuit breaker. So these are all mapped into from there. I think little bit disturbance is coming. Probably if someone could mute himself. I think, is it possible to mute? A little bit disturbance coming, I think, from some of the users. Right, list of wind logical nodes. List of wind logical node. We have WGN, generating system, WCNV, that is converted information, WTRF, wind turbine transfer information, wind control, power control, wind power plant, WPC, WWC, WFC. So these are all the logical nodes. We have meteorological and environmental, WMET for meteorological information, WLG, WALG, these are for analog. Then, of course, we have monitoring, alarms and reports, WREP for report information, then alarms and this kind of things. So typically, we tend to get the these logical nodes and everything mapping like that. Wind speed, wind direction. Suppose we get WTRF.WSPD kind of thing. If we have pitch angle blade 2, so we tend to get WBLD2.PT ANG, some kind of thing. So this is just to give you a flavor that how logical nodes are mapped for this SCADA and for this wind turbine, something like that. So I think this is in this particular 400 series. If you see this, all the particular logical nodes and everything, those are given in terms of in there. So every WTUR, that is turbine general information, WOROT, that is turbine rotor information, then converter WCNV. So this kind of thing. So part 25, it is just like 61850. So we have wind turbine series, we have wind power plant controller, we have substation automation system. So these are all interconnected, and that's the interface. So any wind turbine will possibly have this kind of mapping inherent into there. So any data column names are site names. So ideally it looks like turbine 101/cfg.site.name, something like that. So this is a typical procedure that follows this mapping of this communication system. So, and we tend to have. Now we, that's the part of this thing. Then I would like to quickly go before we start a little bit of cybersecurity, then I tend to go for directly with the SCADA database. I think little time is there still, so just I intend to change the screen. Just bear a moment, bear with me. Yeah, just let me know if it is visible, the new screen.
Yes, sir.
Okay, thank you. Thank you very much. Right. So what is cybersecurity? Cybersecurity these days, I think everyone is aware, because everyone is very much aware of this cyber fraud in the bank scam or credit card fraud, something like that. But what is cybersecurity in terms of power sector? It is a little different because it is OT security. Cybersecurity, conventionally it is called IT, information technology security, but in OT is operational technology security. So that's the difference where it is. So before I start, I would like to show you a simple, quick 1-minute video. There is no sound, probably a little sound. So the background is there has been a test. It's a simulation test called Aurora test. And this Aurora test was performed by Idaho National Lab in US in 2007. And that was the first test when it was first demonstrated that if you could manipulate the SCADA or the PLC data, then end of the day you could damage a generator. So just quickly see this, and that will give you the flavor that what is actually cybersecurity in OT. So once we finish, we'll come back there. So I have started it. It is an authentic from there, Idaho National Lab, but this is something like that. So what they did it here, you just see this, it is 1-minute video only. Yeah, thank you. So you could understand. So what they did actually, they started a DG set, but quickly with the 30 lines of code, I think in 2007, 20 years back. So they just manipulated the signal. So when the breaker is supposed to open, they close it, and when it's supposed to close, they opened it. And just the DigiSet was in the throw-off mode. So end of the day, what happened, you could see. So this is the beginning in 2007, this Aurora test. Of course, if you Google it or IEEE or Google Scholar, you will find scores of information there. But that was the start of cybersecurity in power grid. And of course, later on, Ukraine grid attack and everything is there. But that was the start. So that gives the first flavor why cybersecurity is so important. So with this, I tend to little bit a few slides only, then go directly to the SCADA data. So interoperability, as you know, today smart grid is comprised of many facets, and these are, we have right from social media connected to the substation automation system. In the substation, if we have a PMO, that is also again connected. So these are all the crux of there. The components, stability analysis, AIML, cybersecurity, everything. So this Aurora attack that first demonstrated a device with the ability to open or close the breaker, access to the open or close device, knowledge of power engineering, information about the power system, and the hacking skill. So these all actually govern and form the what we are aware of this cybersecurity awareness today in the OT grid. Now, there is a concept called OSINT, Open Source Intelligence. What is that? This is a cyber threat intelligence actually. Now, this is also, there is given, it's a IEEE paper, I think quite, I think 7-8 years old. I forget this paper author, but what he demonstrated, without having any idea of any utility, these gentlemen, as a scholarly study they made, they just reconstructed the whole grid networks of an entire region. So how many lines are there, how many substations are there, where the feeders are coming in, where it goes out, everything. Not only that, hang on, so they find out which vendor they have for their different equipments. So they find out ABB has 216, G was 458, Schneider Electric has 373, Siemens 271. So what happened, they identified there have been 1174 N-2 transmission link. And I mean, contingency scenario, reduced network, possible 26,000. So they identified which one is the most critical link and how it could possibly be made a particular vulnerable. So that's a very interesting study in terms of OT security of electrical power networks. And the most fascinating part is that what they did, they didn't use any commercial software. So they used everything which are in open domain. So they did a math power contingency analysis tool. Earlier it was there. I don't think they are there. Power system DB, open source GIS, tactical analysis. So everything they find out. So what they did, they reconstructed as if a parallel utility, this data bank kind of thing. So that particular region of data bank, what kind of data they have in there and every possible intricacy. So they narrowed down to a very, very vulnerable exchange. And that's a very alarming situation. So this is something like that, OSINT Smart Grid CTI. I think this is, the link is there. You could find out more information there. Now, so in terms of the security, actually, one thing is important. That's called encryption. Encryption means that when you camouflage some of your data into some different form, and what is the other side of the decryption? So when you decipher that encryption back, so that's the Caesarian text. So you just, earlier it was there, you just shift of some parameter, something like that. But today it is more complex. We have different kind of securities like that. Now, what is the relation in here? In communication protocols, there are several, these protocols are there, just like TCP called Transmission Control Protocol. Also, there had been one UDP, user datagram protocol, something like that. So TCP, we mostly deal with TCP for the SCADA 61850 or for the National Road Dispatch Center, like regional center. They tend to use that IC 60870 part 101, part 104. Again, extensively use this TCP. So these are nothing but protocol. In SCADA, so we have protocols and ports. So what is port? Just like printer port, everywhere through which the internet or any connection of data communication is there, that is called a port. And this port is also not hazardous. Ports are got very specific numbers. So port numbers, one starts in and it goes up to, I think, 60,000, something like that. So in SCADA, we have protocols. We know that there are MMS protocol. We know there are Goose protocols. We have different TCP, IDP protocols. And of course, in terms of that, we also have IT protocols as well. So SCADA mainly comprises, from the communication point of view, its protocols and ports. Of course, it is the architecture that has got hardware, software, communication. We have interface, we have scalability, redundancy. And end of the day, we have the functionality, because SCADA, we know that it operates, it has got distinct functionality like control, monitoring, and protection. So monitoring, control, and protection, that's the main purpose of that, but it ensures through this protocol and ports, and that's the communication profile. So IC 61850 is basically one embedding of electrical, power system networks operating system. And And that's why protocol and ports are important. And of course, there is a WASI model, and this is called 7-stack model. So it starts with application layer. Suppose you are an user, you are doing something in the substation control room. So you are using basically the application layer. And this physical layer is where the CTPT or the breakers that operate. So that's the physical layer, but in between there are many layers. So altogether 7 layers. So this is called OSI layer. So just if you see the capital APSTNDP and the key rows are there. So just to keep in mind that OSI layer that forms the backbone of this communication profile. Now, how data communication comes in? If you see, this is a GIF message, GIF file. So see, there are OSI layer on both sides. So suppose one substation to another substation or anywhere data is communicated. And you see this, it is coming like that. From the application layer, it comes down, presentation layer, session layer, then comes transport layer, network layer, then data link physical. And then it goes back the encapsulation in the reverse order. So sending the encapsulation and receiving, so it follows this format. Now, what's the important thing? In the physical layer, things comes, if you see, that's a quick visual, it's a binary system, 0, 1, 0, 1. And that's how the communication goes. It always transmits in a binary way. So all the layers, end of the day, it's coming through, and that comes into a binary layer. And these layers, see, 0, 1, 0, 1, 0, 1, 0, something like that. So instantaneously, it goes there. And in a SCADA, so what happens, it's a real time, it's called telemetry. That means it operates 24/7 basis, mostly uninterrupted and without any human intervention or minimum intervention, and keep on doing that. And that's where cybersecurity is very important, because end of the day, your physical layer could be hacked, as we have seen through the Aurora test, something like that. Now, what's the OT security then? So OT security is somehow mapped with these WASI layers, but in addition to the IT layers, there are some of the things that is given in there. So it's a quick flowchart and how this every layer is mapped. But what we need to know, we are utility professional, we need to know that how we should protect our grid from what point of this. So some kind of abstraction we tend to have. So that will give you a complete flavor or some kind of high level abstraction. So how we could make this more robust and more authentic and more this foolproof for getting an attack by there. So in this IEC 61850, also there is another series that is called IEC 62351, that is purely of cybersecurity of power system networks. So there is a flowchart, and this flowchart entails that how these are connected through this SCADA system 61850, and how this is mapped. Now, thing is that in terms of OT security, actually, it is called, rather than in cybersecurity, there is a concept, there is a term called triad, CIA, confidentiality, integrity, and availability. Now, in OT security, it comes in a reverse order, because your power system network must be able to transmit and fulfill the end user requirements. So availability governs. So it comes in a reverse order. AIC, availability, then comes integrity, then comes confidence. So you have to manage in that way. So here gives a quick overview of how this is mapped, something like that. Again, 61351 series, it comprises of 9 parts, almost only 10 parts. The part 10 has also come, and it gives everything is there. If you see the part 5, that is security for IC 6870, part 5 and DNP3. And part 4 is security for MMS, that is 61850. So part 6 is goes and sample values. So SB or sample values, it's the SPV. So end of the day, what we tend to have, so these are all mapped. So we need to have a quick flavor of that, because the SCADA data also we tend to have, it is very much, possible that someone could hack the SCADA data at some point of the time, something like that. So IT/OT, how it works, we have feature, we have IT part, we have TLS VPN, and we have the standards. So how it is matured. Now, why IC 62351 series matters for renewables and DER? Because we have high DER penetration, we have remote wind and solar farms. So very likely these wind farms, particularly offshore wind, I mean, it is very difficult to access in town in case of contingency. Of course, we do have unmanned power stations these days in many places, many areas of countries. But at the same time, so it is one of the keystone that these are remotely controlled. So this 61 to 351, it aimed to prevent the fake curtailment commands. It secures the set point updates, time synchronization for protection, trusted remote control. Of course, time synchronization is another aspect. You must be aware that time synchronization through SCADA or PMU, it runs through, in addition to the SCADA protocol, they are also contingent on the satellite timestamp. So again, that is one of the very, 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 very delicate thing. So what IEC 62.351 does not do, it does not define firewalls or network zoning. It doesn't replace actually 61.850. It does not secure physical access. It doesn't guarantee safety by itself. It is one layer in defense in depth. So it specifies how power system communicate, disrupting real-time operation. So how the parts fit together. So that's a quick overview: philosophy, language, client, server, secure communication, fast protection, messaging, monitoring, access control, keep trust, something like that. So mapping OT attacks, IEC 62.351 controls. There could be replay attacks. There could be false data injection. There could be something manipulated measurements. So these are all this part of that. So it is I mean, conjoined to that SCADA data and something like that. And there is also concept of man in the middle. So that is also comes into picture. Time synchronization, there is a concept. Academically also must be aware that GPS or GPS spoofing, that means the GPS, the timestamp or the signal they tend to give, actually it shows something different. So that is why time synchronization attack is also another thing. Inside a privilege house, that's a physical thing kind of thing. So that's the end of the cybersecurity part. So I think now I would like to quickly go through a little bit Google Colab of this offshore wind farm. And then I would like to show in there. Just bear a moment, bear with me. Yes, just a minute, please. Window. Yeah. Just if you let me know that when it is visible, please. Yeah, is it visible, please?
Yes, it is visible.
Okay, thank you. Right, so we will quickly see that what are the SCADA data, particularly based on 61400 series and wind farm. So here it is an onshore wind farm because it is small. So you could input this with the data. So now we have data, and data is we open it with a part of that with CSV file, and then we have different components and we join together that data. We do concatenate with three different this data frame. And now see what the columns are. And the columns are, see the site name, timestamp, turbine ID, active power raw, ambient temperature, blade pitch angle, generator winding temperature, nacelle temperature, stator power, rotor speed, temperature, bearing max, trafo, wind, winding temperature. So these are all part of the SCADA data. I mean, that's the variables actually. So we tend to get that from this SCADA data. So it's the 10-minute basis data, and we tend to get. So these kind of columns we have, and of course every column is treated from the data analysis part. These are all variables. So just one first row of the data, if you see, that's the timestamp, turbine ID, active power raw, ambient temperature, blade pitch angle, oil temperature. So these keeps on going, and altogether I remember probably it is about 300 distinct data variables. So you could understand manually it is just impossible to see manually go through any data at any point of time for any wind turbine. Please be mindful, these data or these columns for one particular wind turbine. Now, in an either onshore or offshore wind turbine, we have at least few hundred, if you say few dozens of wind turbines. So manually, we do not have any scope of intervention. The data keeps on coming and coming and coming. Now, I guess most of you have already quite handsome idea of this data analytics and AI/ML, but in reality, how we tend to cope up or how we tend to deal with this kind of data. So that's I intend to show, and what kind of parameters we tend to derive and something like that, a quick flavor of that. So this gives this in a vertical way data types. You will see this active power raw, ambient temperature, max, minimum, peak angle, then gearbox, oil temperature, something like that. Now we take slice from, this is quite recent data. We slice for a year. So 2024 data for all three files. So we start with 1st Jan and we end with 31st December, something like that. So now what we see, let us come to some figures. So if you see, these are the turbine IDs. So how many IDs there in this farm? I think it was a little over 30 number of wind turbines. So let us see more than 2.5 dozens. And these turbines are termed with turbine ID. So GTB ID 13, GTB 2, GTB 24, something like that. Now, as you've seen, these are the columns. Now, turbine-wise power curve inside. So what we get from the this power curve actually. So these are something like that we intend to see. And then what are alignments. So what is your misalignment? Your misalignment means it is ideal that you have in a WT your alignment, your system. But in reality, whether your system are currently functioning or not, that we are unsure of. So that gives with some kind of thing what your error actually. So this with the data analytics you could get in that what kind of there. Now, this is something called power curve by turbine wise. So if you see, this is turbine wise. So every turbine, all 30 turbines, so it is given. So power curve is nothing but based on the horizontal axis, it is wind speed, and on the vertical axis, it is active power. So this gives you different flavor. Now, when your power turbine is functioning well, this is a 2 megawatt turbine. Yeah, everyone, and we have about 30 numbers. So total capacity is slightly 60 megawatts, something like that. And every power curve is something like that. So when there is no power or something like that, so definitely that gives a combine. So in your dashboard, when you have a particular this AI system for managing all these turbines for a particular wind farm. So you tend to have this kind of, on a real time telemetry basis, this kind of insight from there. So what the turbines are there, what the power curve is, real time it is generating, whether there is a fault in there. If there is fault, then what the reason for this particular fault, something like that. So your misalignment, so we could find out depending on the different variables what your error comes into picture, a little bit of coding, and that is possible with get your error. Now, what the inference from there? Less than 5 degrees, that means that your error is excellent, or we could say with some kind of confidence these are quite well aligned. If we have 5 to 15 degrees, it's common, however, usually okay. But if we have 15 degrees, likely needs some kind of investigation. So that's a scenario we could have. So if we have this number of 30 numbers of wind turbine, and if we have a data analytics for your misalignment, then you could find out on a real-time basis So what is the misalignment? Then you could, aware of that what kind of prevention or precaution we need to carry out. Next, gearbox temperature and gear generator thermal health. Let us see what it says. Entails. Identify turbines running hotter. So here we tend to have a thermal column, that means gearbox oil temperature, winding temperature, and of course there are three winding 1, 2, and 3. So we tend to get what turbine IDs, turbine ID wise, what these temperatures are and how they are keep on going, and what kind of analytics or what kind of insight it could produce us for getting this kind of thing. In summary, gearbox oil temperature 56.7 degree. It is considered safe. Generator winding temperature 75 degree approx, normally balanced. So if we consider for a particular turbine GTB 20, so we don't think for that data particularly no abnormal thermal behavior. But what we intend to say with this kind of analytics, actually we tend to identify which turbines are running hotter. That means how it is possible to identify. So it is some kind of prevention mechanism, just like those operation and maintenance. You are aware there are maintenance policies, and in the maintenance policies we have either preventive maintenance or breakdown maintenance. So we could use, with the use of this data analytics, that some kind of preventive mechanism. So that means what I intend to say is that these data analytics in a real world scenario, if you have a wind farm, that give you some kind of confidence how to use for your particular own domain. That means in your, as a grid operator, if you are an owner of a wind farm, so you must be in a position to understand what is your wind farm current scenario or current regime. At the same time, what is going to have after some time. So that means identifying, rather forecasting, that what could likely be a possible fault and whether you could aim for rectifying that. So that is the aim of this. So we tend to identify which particular turbines is running hot or something like that. Temperature versus active power. So thermal derating. So here we tend to have, depending on again all the turbines, that gearbox temperature, oil temperature, and on the horizontal axis, x-axis, we have active raw power. So what the power is. So what is the active temperature? On the left-hand side, if you see, most of the scatter points are concentrated on these points. And if you see, and this is going on slightly upward trend. So our job is actually to find out not only this curve, what the pattern is, but at the same time, whether these patterns are any way normal or there could be some trace of anomalies. If there have been some anomalies, how we could find out those. So these kind of analytics, simple scatter plot, but on a real-time basis, because those who are aware in real-time basis, often wind farm operators, they, if they don't have the bigger level software system, because Microsoft Azure, they have a specific capability for wind farms. So those who use Azure Wind, they might be aware they have. But at the same time, if you have your own wind power system, so you could have your own this data analytics or AML paradigm where you could use your own thing. But end of the day, it is all about the real-time data. So that means it's the data is coming at any 10 or 15 minute interval for this 30 number of turbine, and in a continuous speed and continuous fashion all along for the operation of the this wind farm. So that is something we have to be very careful, because we don't have the luxury of going through each and every variable. The only thing we have to rely upon is how the system could be automated, and that's why we tend to have. Next thing is rotor and generator speed anomalies. Here we tend to have what kind of anomalies it could have. So we tend to have what the speed ratio. That means whether that ratio is something manageable. If it exceeds a particular threshold or going beyond something like that, so we tend to get something like that. So this is rotor or wind generator. Speed anomalies that we also have. So meaning of speed ratio means generator by rotor speed, how fast the turbine blades are spinning, generator speed, how fast the generator rotor are spinning. So speed ratio is the ratio between the generator and the rotor, because you know that in the rotor there is also a stator part, so anything could be vulnerable for any kind of malfunctioning at any point of view. So here we tend to have this real speed and generator speed, and we tend to have the real-time basis ratio of something like that. Pitch system analysis, as we have seen, every blade we have in turbine, we have 3 blades. So every blade tend to have some kind of pitch, whether that pitch is erroneous or something like that, we tend to have that. That's a pitch system analysis, and we tend to do with some kind of thing to get some kind of this insight from there. So what the pitch is, so 0 to 5 degree, as we said, near rated, above rated 10 to 20. So cut out, cut in 90 degree, and lightly expected that is shut down. Transformer winding temperature trend. What kind of trend we could have? We have trafo columns in the data, the SCADA data. So if we get that, so that gives the overall insight for which particular trafo or which particular winding. As we are aware that in a particular trafo there could be many winding, 1, 2, 3, or even more for a higher turbine size, so that we could gather some kind of insight from there. In summary, 65 degree mean, typical for normal operating transformer winding. This is well below max safe limit. So that's based on that data inside, it says the wind turbine is going more or less healthy. Reactive power and power factor stability. So that's another point we could find out. So we find to have what the power factor and stability. So that will give an overview that whether we could improve or any kind of scope is there for rectifying this power factor, improving the power factor, something like that. So these kind of things, of course, power factor, we know the ratio. So all the data are there. We could find out any specific, if any sensor gives some kind of warning or alarm, that we could get something like that. So what the aspect is, grid code compliance and impact, reactive power control, apparent power, fault detection. So these are all inherent there. Operation state diagnostics, how we could send there. Again, we could have the proportion, some kind of thing, again, based on the data. So you have the data, you have your domain knowledge, you have this. So depending on the fraction, you could finalize whether the operation state is whether it is running, standby, fault, or something like that. So these are some kind of operation diagnostics. Now, if you statistically intend to see what the turbine-wise correlation inside, you could get what the correlation between different parameters, wind speed versus active power raw, gearbox oil temperature, blade pitch angle, active power raw. So these are all kind of things that you could see turbine. So this is a list for all the turbines for that particular wind farm for that particular point of time when it was functioning well. Underperformance ranking, this is very much essential for finding out which particular power is likely to go at some kind of fault, something like that. So here it is underperformance ranking, some kind of mechanism it is possible to get and something like that. So these kind of things are quite common. If you see the turbine ID unique, GTB 01 to GTB 30. So we have 30 turbines and all the data are coming. Now let us go for a slicing of a particular turbine. So I understand time is short. So let us see whether we could get some kind of figures, power curve, something like that. Yeah, that's a particular curve, and this is the binning. Binning means for every 0.5 meter, what the IEC says, the power curve. So these dots are actually binning. So that means you could refer your power curve whether it is running healthy or some kind of there. Now this gray area, this is 95% confidence interval. That means you have a range of plus and minus of that. So that you give whether you are getting the actual power is within that range or something beyond. So this particular turbine with binning, so raw sample bin, confidentially limit, something like that. So these kind of this analytics you could get, and depending on, of course, you could change the colors, coding, and something like that. So these are. So this is thermal stress plot. So again, you could get some kind of thermal stress plot to see the bottom where there was fault and turbine was shut down. So this is some kind of threshold, and based on that thermal stress plot was there, and that is all together. So thing is that it keeps on going inside. So when you have and some kind of this anomalous behavior, so end of the day, your intention is to get some kind of, if it is possible, to have some kind of this predictive analytics or idea inside from that. So your mismeasurement, something. So there are scores of things. I think it is 218 page. Probably, I think some other, you have some other course as well. So I would like to end up in here. And if any question, then I would be happy to have you there. Thank you.
Thank you, sir, for your very much, sir, for your sharing your global perspective and experience. We'll now open the floor for questions. Participant, please, if you have any doubts or questions, you may ask.
Sir, as per your opinion, what is the future of a small wind turbine
Yeah.
in India?
What is the small wind turbine?
Yes, sir, just like Germany and Switzerland are building a small wind turbine nearby roadside or rooftop.
Small, in India nowadays wind farm is there. I mean, not offshore, but onshore is there. There are many companies, those who are building winds, onshore wind, and they have, this data is from actually real world data. This is, I can't name what the data from, but it is a real world data for 2 megawatt wind turbine. For every 30 turbine is of 2 megawatt each. So one turbine is probably very common. If you travel towards Rajasthan, these areas, you could see many turbines.
Participants, if you have any other questions.
How the phasor misalignment are being detected?
Sorry, say again. Your voice is little bit unclear.
Okay. Phasor misalignment.
Phasor misalignment.
Yes, you said in one slide. Am I correct? Or
Your misalignment. Phasor is something different. Phasor comes in PMU, phasor measurement unit.
no, here also in your presentation, I found somewhere it's the alignment issue you show.
Yeah, that's mostly alignment issue or yaw alignment. Yaw is, that means the pitch angle. So that you have the data. In the data, if you have a SCADA system, that SCADA system tend to give all the data. So only thing you have to apply your own this criteria. So those data will give. And of course, you have the flexibility of doing that in your own coding, because in real-time system, if you have a system not like Azure, suppose you have a particular new software system for a specific vendor. So you could build your thing. Suppose I am aware that some companies, even in India, they tend to have this
Okay.
real-time world with
Another
price stuff.
another issue you said, the fake curtailment.
Okay, okay, yeah, fake curtailment.
Fake
Yeah, that's
curtailment.
little bit
How
of, little bit
how
of,
these things are being detected?
it is a little bit of cyber security, you know. Time is a
Yeah.
constant, so I had to cut short that. So that's why I intend to give the flavor actually. It is
Okay,
detected.
no issue, no issue. From there itself, I also saw that phasor misalignment. It was also there. These two terms, how it is being detected in there. Okay, no issue, no issue.
Okay, yeah, okay. I will see there. If in your slide is something particular there, then I will tend to. I will send to Dr. Bhaumik. Then
Okay,
I
no,
probably will get back. Okay, thank you, thank you.
okay. Other participants, please.
So other participant, please. If we don't have, so we can close the session 12 officially.
Yes,
And
please.
thank
Yeah.
you, Mr. Biswas, for your kind consent and giving insightful thoughts.
Thank you, thank you.
So now participants are requested to open your camera so that we can take a picture of your session 12. Thank you all.
Okay, bye bye. Happy learning.
Thank you, sir.
Bye.